Hello, and welcome to my talk on prefetching in functional languages. So what this basically is a look at the way programs written in functional languages, particularly OCaml in this case, end up interacting with modern hardware, both more generally and especially with the memory system. Then we're going to look at techniques to improve the performance of this in software by adding prefetching as a language construct. And we're going to look at just how important the hardware prefetcher, often designed with imperative language features such as arrays and matrices in mind, actually how important this is to the performance of even linked list heavy code in functional languages. Okay, so to motivate all of this, we're going to look at the simple function on screen. Don't worry if you don't understand OCaml, the code in this talk is also going to be demonstrated via diagram where appropriate. So what we're doing with this left fold operation is adding together tuple elements from a linked list. Though we'll also look at equivalent code on arrays. In this case, the tuples are being indirected to by pointer from the list itself, and each linked list element is also connected via pointer to the previous one. The reason we're looking at this code, executed over a large 100 megabyte list designed not to fit into the cache and thus reside in the computer's main memory, is to observe its performance. And what we see on this slide is that even with this simple code, the distribution of the input list completely changes its performance. If we execute over a list that is being accessed in the order it was initialized and thus allocated in, on both arrays and lists, this operation takes about 0.1 seconds. However, if we repeat that on data that has been reordered via sorting it, then the exact same code on the exact same data is suddenly 6 times slower. So what's going on here? When we first allocate such a list, it goes into a 512 kilobyte bump allocated minor heap, which once full gets pushed out by a garbage collector into the much larger major heap. Because these elements were allocated contiguously, they're also likely to be stored relatively contiguously in memory, even if this isn't guaranteed since the pointers between each linked list element allow them to be stored anywhere. When we sort these, we end up with a new list being allocated, again roughly sequential in memory, since the old one was immutable, and the old one gets garbage collected away. However, the pointers to the element objects themselves are now significantly reordered, resulting in very complicated patterns in terms of memory accesses. These can't be predicted by the hardware prefetcher, which looks at address patterns to predict future accesses, and so we're exposed to the full latency of our off-chip DRAM main memory. If we take a look at arrays instead, then contiguity of the array itself is enforced, unlike in the list case, as an array is a single block of memory. And since arrays are mutable, we can potentially sort that array in place without performing any new allocations. Still, we end up with a jumbled pattern of indirected to objects, and thus we see the exact same performance loss that we did for the linked list on any subsequent operations over the array. Another surprising performance effect that such code can exhibit is if, instead of just a simple addition, we add more complex computation in the way. The example on screen replaces the addition in our left fold with more complex hashing, where we perform a variety of shifts, multiplications, and Boolean arithmetic, resulting in far more compute operations per loaded object. The surprising element here is that on the original allocation ordered data, this only adds another 0.1 seconds of compute to the total. And yet, the exact same number of operations and the exact same code adds a further 0.5 to 0.6 seconds of work to the version with sorted data. What's happening here, paradoxically, is that adding this extra compute is making our sorted version even more memory bound than it was before. So what's going on? To work that out, we need to look at the structure of a modern out-of-order superscalar processor. In such a processor, instructions are reordered in the middle of the pipeline, buffered before execution in the issue queue and after in the reorder buffer, and all executed potentially in parallel. That means we can have many loads going out to our high latency main memory at the same time, even if, as we saw earlier, we still can't perform enough loads to entirely hide this latency and thus suffer some performance loss. However, when we add more compute code, that takes up slots in the issue queue and reorder buffer, meaning there are fewer candidate loads that can be executed at the same time, thus decreasing our out-of-order processor's limited ability to hide latency even further. That's why on a modern out-of-order superscalar, adding more compute can actually make code like this more memory bound. So, what can we do to get around these limitations? We can issue non-blocking loads or prefetches that tell the hardware what it should be fetching in, so that these high latency accesses to memory can be overlapped and the data can be placed into our fast, close to the CPU L1 cache by the time the program actually decides to access it. So, in the array example on screen, we first issue a basic prefetch by jumping ahead in the array, finding out the address of the element several iterations ahead, and issuing a non-blocking load for it. We do this by adding a new prefetch intrinsic into the language, which is lowered down to a non-blocking load in the assembly. However, that access in the array may also cause a cache miss, adding latency to our prefetching operation that will slow down the CPU. So, we also issue a prefetch to a future part of the array itself, so that we can stagger our prefetch access to it and miss on neither once we're ready to actually access them. To do this, we add in a new special array prefetch intrinsic designed to issue a non-blocking load to any index within an array without directly accessing the associated data. As it turns out, this is still useful even when the hardware prefetcher is switched on, which it is by default in all of our setups, because even though this particular pattern is likely to be picked up by the hardware, we can prefetch more aggressively in software. When it comes to linked lists, our job is slightly harder. We can't jump arbitrarily ahead in the linked list, as we have to walk through each pointer sequentially. Still, we can prefetch ahead by doing this sequential walk. The easiest way to do this, which we call simple prefetching, walks a few elements ahead before prefetching the jumped off element. Then, we repeat all of these list jumps staggered by 1 on the next iteration, so that we can this time walk one element further ahead and prefetch the next. This clearly involves lots of repeated work, but actually works better than you might think, because the linked list elements are often roughly sequential in memory, therefore walking them is cheap, and so critically the slow operation, which is fetching the pointer to jumbled up element, that can be prefetched to hide the latency. Still, we can do better by eliminating some of these redundant walks. We do that by storing some information in a process we call complex prefetching. Here, we pre-walk the list and store the high watermark, the latest point we've prefetched from. Then, we can jump off the end of that stored list element on the next iteration, issue a prefetch, and store the next element for the future. By storing these elements to jump off from, we increase the arity of our functions. They will take one more parameter, which is that high watermark of the list, and so the resulting code is more complex, but less redundant work is done as a result. Finally, like with the array specialized prefetch, we need to do something about prefetching the list walk itself rather than just the elements. Unlike in the array, we have no guarantees that these will be stored contiguously. Still, we know that parts of the list are likely to be stored somewhat contiguously in memory, so what we can do is speculatively jump off the end of our current element. This is likely to land on either the element that we want or another element that we'll need in the near future, and thus serves a similar effect to what we do on arrays. We do this using a new intrinsic, prefetch offset, to fetch at an offset from the current element, rather than the standard prefetch intrinsic, which just fetches the current element. In fact, we use that standard prefetch intrinsic for both basic and complex list fetching, but need a new one for the offset prefetching. Now, let's have a look at some of the resulting performance numbers. For Intel Haswell, a fairly standard out-of-order superscalar microarchitecture, we see reasonable speedups on both lists and arrays for the basic sum case, but much larger speedups for the same code and the same prefetches when extra computation is added with some hashing due to the issue queue effects we talked about earlier. For linked lists in particular, we see that the final bar, which encompasses both complex and offset prefetching, is needed for the best results, even with our hardware prefetcher turned on, but even the simple prefetching with lots of redundant walking still gains us quite a large speedup. For the Cortex-A53, which is an in-order architecture, we often see larger speedups for the basic sum cases. This is because the architecture is unable to reorder memory accesses itself without prefetching at all, and so is much more latency bound without our new techniques. On the flip side, because there is no issue queue to clog up to begin with, the speedups are similar regardless of how much extra computation there is. Finally, for the only mildly out-of-order superscalar Xeon Phi Night's Landing, while we still see large speedups for the compute-heavy versions, the basic editions see slowdown from adding software prefetching. This is because, unlike the A53, it can parallelize some of the memory accesses itself, but unlike Haswell, it doesn't have large issue and reorder buffers, and so the prefetchers and original loads compete for the same resources. Those are the results for the left fold we looked at earlier. In the full paper, we show more speedups and analysis for the rest of the OCaml linked list and array library code, but now, let's briefly talk about look-ahead distances. Clearly, if we fetch at too low of a look-ahead distance, then we won't be able to hide all of the memory latency, and thus performance will be suboptimal. On the other hand, if we fetch too far ahead, then by the time we actually access the data we require, it will have been evicted from our cache by other data. Our prefetch will have been too early. We see that the optimal here, recorded on Haswell, for the simple prefetch on the array workloads is at 16, whereas the prefetch into the array itself is fetched at twice that distance. But the graph is relatively flat and a wide range of values work well. For list simple prefetching, the curve starts out relatively flat before rapidly diving downwards. But this isn't actually because we're fetching too far ahead. Instead, it's because it causes more repeat work to be performed by repeatedly walking 32 elements ahead, for example. If we instead look at list complex prefetching, where we store our look-ahead elements for later, then we see a curve that is extremely flat. In fact, because a range of values work, we use the same look-ahead distances for each workload and microarchitecture, despite their very wide differences. The key point is that being close to optimal is very easy to achieve, so complex tuning isn't really needed in order to get good performance. It's not just accesses of sorted data that can be improved using prefetching. The act of sorting itself jumbles up data and causes the same effects in intermediate data. On screen, we see how we can prefetch the partitioning function of a quicksort. We can look ahead in the list we are splitting up and fetch the elements we're about to compare against for our partitioning. On the flip side, in a merge sort, we do the opposite, and we prefetch from both sublists that we're about to merge. Whenever we consume an element from a sublist, we walk one further element ahead in our prefetch of that particular sublist. This gives us some fairly significant speedups, even despite the fact we're only prefetching on parts of the whole sorting algorithms themselves. Next, we look at a benchmark suite we created for the purpose, where we found general OCaml code that was measurably memory bound by using perf to profile it. The full list, the techniques we used, and the description of the workloads are on screen now. We won't go into them all in detail, but they cover a variety of array and list-based patterns. And if you'd like to read about them in more detail, you can pause the video now if you're not watching live, or take a look in the paper. We see that Graham scan, which uses a sorting algorithm as an intermediate on lists, gains speedup just by using that prefetched sorting algorithm from earlier. QuickCall, also on lists, uses a similar partitioning algorithm to the quicksort, and so can be prefetched in a similar way. CG-AddLists and SPMV-CSR are both indirect memory accesses over arrays, and SPMV-CSR in particular shows large speedups on A53, where the hardware isn't able to parallelize these memory accesses without software prefetching due to its in-order execution. HashRead shows large speedups on the out-of-order cores due to having a large amount of hashing computation per memory access, limiting the existing load reordering hardware. Going back to some of the list and array library code, here we take a look at the effects of hardware and software prefetching combined. In all other experiments, the hardware prefetcher is always enabled, but on Haswell, we can turn it off and see what happens. Critically, this is on the original unsorted data, where we expect things to be nicely laid out in memory. We see that having no prefetching at all drastically hits performance. Perhaps surprisingly, the hardware prefetcher is even more important for the list-based workloads than it is for the array-based workloads, even though the hardware prefetcher is designed to pick up the regular patterns exhibited by arrays and dense matrices. This is because, at the dataflow level, each access to an array is independent and can be accessed in parallel, and thus out-of-order superscalar hardware can overlap such accesses. On the flip side, with linked lists, there are true data dependencies. The next element can't be fetched until the value of the current one is known. That is, unless you speculate on the address you're likely to see. This is the sort of speculation that is endemic to a hardware stride prefetcher, but it isn't done by the out-of-order hardware itself. And so without the hardware stride prefetcher, performance drops dramatically. We see similar patterns on the sorted versions as well, where the hardware prefetcher still helps us for the sequential array walk and the fairly sequential list walk. Okay, so that was prefetching in functional languages. We see that in languages such as OCaml, where linked lists are frequent, data is often indirected to by pointer, immutability is common, and garbage collectors are used. We see very distinct slowdowns in certain cases when we work with large amounts of data. Still, a significant amount of the performance loss from the resulting memory-bound code can be regained using software prefetching. On the flip side, the existing hardware prefetchers in today's systems are perhaps even more vital to the performance of functional languages than they are for more conventional imperative languages, as the linked list dependencies can be broken speculatively by a hardware prefetcher in a way that other parts of the hardware can't handle. Thanks for listening, and if you have any questions, please either stay for the live ISMM session or send us an email. Thank you.